for one of the last parallel session, at least the last in the last time slot before the ending of this conference. So let's start slowly, I'd say. Welcome everybody. This is the parallel session number 11 about mitigation, impacts, and adaptation. It's we're gonna have a fourth speaker today here in the session that I will introduce just before the presentation. A couple of housekeeping rules. Please keep your microphone shut while you're not speaking or you're not intervening. If you have any question, please feel free to write down in the chat. Then I will read it out loud during the Q&A session. Every speaker will have approximately 15 minutes for their presentation, and we're going to give approximately 5 to 10 minutes after each presentation. So you're free to write question in the chat during the presentation or just afterwards. And then if time allows, we can continue the discussion in the last minutes of the session. The session today is again about mitigation, impacts, and adaptation. I believe it's one of the most important aspect and maybe missing uh, items that we still have to grasp an understanding about the different linkages between these three topics. Just let me introduce myself. My name is Stefano Granati. I work for the DG for European Commission, for the Director General for the Action for Climate. So we are very much interested in everything that links, both to the mitigation, but also the adaptation, because somehow we'll have to live with some slightly climate change, unfortunately, but also all the linkage that can happen between the climate and, for example, the energy system. We have had a very nice and fruitful discussion in the last couple of days, and I hope that this will also continue in today. Without further delay, I would like to already introduce the first speaker of the session. So his name is Youssef Al-Mullah. He's a PhD candidate at the Division of Energy System Analysis at KTH Royal Institute of Technology in Sweden. Previously, he has he's been working with the United Nations Economic Commission for Europe, and now is also collaborating with the FAO, the Food and Agriculture Organization. His research area focuses on implementing the climate, land use, energy, and water strategies. And today he's going to present about hydropower and climate change, insights from an integrated water energy modeling from the dry basin. So I'll invite Youssef to move to the virtual stage and open his camera if you would like to, and start his presentation. Thank you. I'll
Thanks,
stop sharing.
Stefano, for the nice introduction. And hello, everyone. Meanwhile, I'll try to share my screen. I hope you can see it.
Yes,
Thank you very much. And again, it's a pleasure to be with you and to introduce or share some of the insights from this study on hydropower and floods, and some of the insights from the Dreen River Basin. In this analysis, or before we start, let me give a few introductory words about the Dreen Basin. The Dreen Basin is one of these transboundary basins, which means it's shared between different countries, and it's in Southeast Europe, shared between Albania, North Macedonia, Montenegro, and Kosovo, and a little bit also in Greece. The Dreen covers an area over 14,000 kilometers square, and it's home for about 1.6 million people. So it's a large population that depends on the Dreen River for different socioeconomic activities like agriculture, tourism, and others. Climate change has affected the basin significantly, as many parts of the world, of course. And in recent years, the frequency and the intensity of floods in the basin has been increasing. And this caused large damages, several millions in some of the estimates. Hydropower is one of the main ingredients of electricity generation in the basin and also in the region in general. So all the countries rely heavily on hydropower to a great extent, and the basin itself contributes by about 2015 megawatts of hydro capacity. If we take this 2015 and put it in context, so it's about 50% of the hydro capacity in the region, which means in the three countries, and also it's almost one third of the total electricity if we take into account thermal generation and other non-hydro renewables. So it plays an important role in the security of electricity supply in the countries. Along the Dreen River, there are five large hydropower plants and large reservoirs connected to those. Two dams and hydropower plants along the main tributary, which is called the Black Dreen in North Macedonia, and three hydropower plants and dams are in the Albanian part along the main Dreen River. And those five hydropower plants are the focus of this analysis because those are the ones that are affecting the mainstream and they have the highest impact in terms of the flooded area downstream. This study has been developed under the Memorandum of Understanding for the Sustainable Management of the Dreen Basin. This was signed between the riparian countries in 2011, and since then they launched several cooperation activities ranging from data sharing, from meetings, from conducting different studies, and so on. And one of them is the Water Energy Food Nexus study that was conducted under the supervision of the United Nations Economic Commission of Europe and the Global Water Partnership and funded by the Austrian Development Bank. And if some of you have joined the session just before lunch, the colleague from UNECE, she also put this into the context of the different analyses that were developed under the Water Energy Food Nexus with the UNECE. And within this big Nexus umbrella, we focused on the water energy aspects and on the flood and hydropower interlinkages, developing a modeling framework that was developed by KTH, our team at KTH, and also with valuable inputs from Polytechnic University of Tirana. And in this analysis, we aim to quantify the costs and the benefits of what we call a flood smart or a cooperative hydropower operation along the basin, which means both hydropower plants along the cascade in the Black Dreen and the main Dreen River basin, to see if we improve the operation or change a little bit of the operation of hydropower plants, will that impact the flooded area, or will we have some sort of savings in terms of flood damages? So that was the whole idea about developing this modeling exercise. So of course, when we are talking about hydropower and playing with the operational rules, we need to face the problem of, okay, this will impact our security of the electricity supply. And if you are going to change how we are operating the dams and how we're filling them up or emptying them in certain different times, of course, this will have impacts for the electricity, and the utilities are concerned in this perspective. So this is one dimension that we wanted to look into, and that's why we used an energy model for that. And also in terms of the flooded area, which is the main story here, is how much we will have in terms of how much we will save in terms of flooded area and flood damage, and how much we will gain in terms of storage capacity in these reservoirs. To be able to achieve the goal of this analysis, we integrated two modeling frameworks. One is the hydrological model called Pantari, and this model has been developed under this memorandum of understanding between the riparian countries that I mentioned, and it was developed in previous sets and previous projects, but it is kind of detailed and specific for the Dreen context. So we were very lucky to have such a model ready to be used and updated in this analysis. And we integrated Pantari with a long-term energy systems model called Osmosis, which stands for the Open Source Energy Modeling Framework. And by integrating those two modeling frameworks together, we were able to explore a number of scenarios. something related to the baseline, the current level of cooperation, and how the current dams are being operated. Is a set or subsets of scenarios related to climate change and different RCPs, and how that would kind of affect the water and the electricity supply. Something related to a new dam scenario, which is upcoming in Albania, and this has a larger storage capacity and is affecting, of course, the electricity supply. It's affecting the storage levels and also the generation from other hydropower plants, and the flood protection scenario that I would like to focus in this presentation. So in the flood protection scenario, the key question here is, can we achieve a better flood control if we increase the buffer volume in the reservoirs? And what would be what are the trade-offs with the electricity generation? And when I say the buffer volume, I mean this empty spot or the empty volume that's usually kept empty in the reservoirs in order to have enough storage capacity in the occasion of a flood. And this is regulated by the operational rules of the hydropower plants. For the dream case, these operational rules have been set since the 80s and they have never been revised. And most of the utilities are or the two utilities that are working there, they are kind of following or not following those operational rules. So we try to look into these operational rules and try to think about different way of operating the dam and increasing this buffer volume. During the analysis, we realized that there are two, out of those five, there are two which are more critical. One is in the more critical in terms of their impact on the flow in the Dream Basin and also on the flooded area. And one is the Shfilia Dam, which is in North Macedonia, which means it is a bit upstream. And then the second dam is Fierza, which is just after Shfilia, and it's the first dam in the Albanian part. Of course, the storage capacity and also the electricity generation capacity in Fierza is much higher than Shfilia. So we focused our analysis on changing the operational rules of these two dams, and we explored a number of changes, like what will happen if we increase the buffer volume by 5%, 10%, 15%, and 20%. And in this analysis, I will focus on the two extreme cases, the 5 and the 20%, because they show a little bit of more interesting results. And of course, we applied these changes in the wet season. So the operational rules during the dry season has not been changed, but we focused only on the wet season from October until May. When we change the operational rule and increase that by 5% and 20%, of course, we will gain additional storage capacity, and this varies depending on the volume and height curve in each dam. So in Shfilia, as we can see in the graph to the left, we can see that changing by 5% will add additional storage capacity ranging from 7 to 9 million cubic meters. But if we go to 20%, then we will have higher savings or additional volume that can be used during the flood, which ranges from about 26 up to 34 million cubic meters. In Fierza, which is, as I mentioned in the previous slide, has a higher storage capacity, these savings are much significant and ranges from somewhere like 36 million cubic meters up to 270 million cubic meters in the month of October, for example. So this indicates that we will have significant storage that can be used during if any flood happens in this period. And the question next is, okay, what would be the impact in terms of electricity generation? And here where the energy model can help us. And I need to mention that in the energy model, we modeled the entire electricity system of all the riparian countries, which means not only the 5 hydropower plants that I mentioned, but all the hydropower plants in the basin and also outside the basin, other renewables like solar, wind, and also the thermal power plants, in addition to the electricity import and export interconnection connectors.
Yes,
The,
Yusuf, you have
yeah,
just 3 minutes left if you wanna.
yes, yeah,
Yeah,
sure.
that's what. Thank you.
So the interesting thing here is that the impact in terms of electricity generation were very minimal. So in the case of Schwilia, there were the annual change is about 5 to 8 gigawatt hours a year, which represents a very small portion. And in terms of in Fierza, this is about again 5 to 34 gigawatt hours a year, which is in the range of 2% annually. And if we look at the bigger picture in terms of the entire Dream Basin, we realize that the other hydropower plants are compensating. So the entire basin, the changes are very negligible, which gives us a strong message. And this can motivate the electricity utilities that you will not lose anything, or the losses will be very small if we play or we revisit the operational rules. Quickly, if I just look at the second part of the story, which is okay, what will happen in terms of the flooded area? The outputs of our model were sent to other models that looked into the flood damage modeling, and we developed some maps. So this is for a 20% increase. And if we compare a reference scenario with a scenario with a 20% increase, we see that there is a significant change in the water depth, which means that we are reducing the flooded area downstream. And if we put this into monetary values, the results show that the impact of this changing it to 20%, will reduce the flooded impact and monetary value by 30% in Montenegro, which is roughly about 300,000 euros. But in Albania, this can go up to 17.5 million euros, which is 60% of the impact, based on the numbers that we use in this analysis. So by this, I would like to wrap up that changing the operational rules from this study, we saw that it has a very minor impact on the security of electricity supply. However, it has the potential to give us a additional and a significant spare volume to be used during flood occasions. And we saw that the savings in terms of the flood damages are considerable and worth to initiate the dialogue and the discussion with the electricity sector. So the energy sector has an important role to play, not only by introducing more renewables, but how we are operating the renewable capacities and the infrastructure that we have today can make also a significant difference. Thank you very much for listening, and hope I haven't exceeded my time. Thank you.
Thank you very much, Yusuf. No, it's perfect timing and a very interesting talk. I'll invite the people on the public to write their question on the chat, if any. I don't see the question on the chat, but I have a very quick one. I see that you project some some economic savings in terms of the flood management. Sorry, when what's the year for this projection? Is it like considering today's situation, maybe 2030? I don't know. What's the year for this economic savings?
Yeah, I need to mention that this is something that was done after our work, and this was translated to other colleagues from other projects that took the inputs and they developed based on their kind of flood estimation that took the values from the recent floods that happened in 2014 and 2010. But how these projections that they represent 2030 or beyond or before, I don't have a clear idea about that. But what I can say is that the monetary values were based on the latest floods that took place in 2014 and 2010.
Okay,
Yeah.
perfect. So thank you very much. In the meantime, there's a question from Jan Holland. What is the monetary equivalent of the -2% electricity reduction? Do you have this
Yeah,
figure?
that's also a good question, and this is something that we the values, the actual values for the electricity generation, we couldn't find these values. Even we had the dialogue with the stakeholders and the energy utilities, but we didn't really get to that point where, okay, we have the actual monetary values for how much it costs these utilities to produce this electricity. So we don't have the actual values, unfortunately.
Okay, perfect. Thank you very much. For the sake of time, I would like to move to next speaker. But before, thank you very much, Youssef, for your intervention. And I invite the public, to write question in the chat. We might have some time at the end of the session to ask further question. Thank you very much, Youssef. All right, now I'd like to move to the next speaker. I think he's Francesco. He say that there was some problems, but I think he's online. So can you hear us? Can you?
Yes, I can hear you. Can you
Okay,
hear me?
perfect. Perfect.
Perfect.
That's great. Okay, next speaker is Francesco Colelli. He's a PhD student in the Science and Management of Climate Change program at Ca' Foscari University in Venice and the Euro-Mediterranean Center of Climate Change. His research focuses on the relationship between energy demand and climate change adaptation strategies. And previously, he worked also at the Institute of Energy, Environment, Economics and Policies and at the Center for Research in Geography, Resource, Environment, Energy and Network at Bocconi University. He will present a paper on air conditioning adoption and electricity demand, implication of climate change adoption on power system resiliencies. So, Francesco, the stage is all yours.
Good afternoon, everyone, and thank you very much for the introduction. So I'll share my screen and let me just have a second. Yes. Okay. And let me show you. Can you see the presentation?
Yes, we can see. Yeah, perfect. It's
Okay,
also in
perfect.
presentation mode.
Perfect, thank you. The study we'll present today is indeed focusing on the implication of adaptation action to climate change through air conditioning adoption on power system resilience. In particular, we wanted to look at the implication on peak electricity demand. And this study is co-authored with colleagues at Ca' Foscari and CMCC, in particular Professor Enrica Dechan, and with Professor Ian Suwing at Boston University. We are focusing on this topic, and we believe it's important because already today, air cooling constitutes an important part of peaking electricity demand in tropical as well as in temperate economies, particularly in temperate economies right now and developed economies. But the growth in tropical and developing regions is telling us that we really should look into what drivers into the future may shape this the importance of AC in electricity demand. And also because we already see that during extreme temperature events, during heat waves, sharp fluctuation in electricity demand for cooling are putting pressure on power systems. And we have records of this in some European cases and also in the US, for instance, in California. So empirically, what has been done so far has been understanding the covariation between peak electricity load and weather, and then using future weather forecasts and or climate projections to infer how the peak load will evolve. What has not been done, according to our review, and that's why we are conducting this study, is factoring in this load to weather covariation also the future increase in appliances. So we are when we look at the covariations in the short term, we typically refer to this mechanism as intensive margin, whereas when we instead are able to take into account the long run effects driven by adaptation of population over time, in our case, it would be essentially through the acquisition of new appliances, then we refer to this adjustment as extensive margin. So intensive is short term and extensive is longer term. And typically, the literature has focused on the former rather than the latter. And in this study, we focus on two different regions. Although most of the results I'll show you are focusing on Europe, we actually conducted this study for two very different regions because we wanted to exploit also the variation between socioeconomic and climate characteristics of both Europe and India. And we collected data at the member state level for Europe and at the state level for roughly 30 Indian states. And we collect data on the daily peak load and total electricity demand. And we match this data with daily population weighted exposure to maximum temperatures and slowly varying seasonal, usually quarterly socioeconomic variables, so per capita GDP. And finally, the key variables that we also track in the data set is the prevalence over cooling in the household, in the residential sector, meaning the total, the rate of ownership in a given region in a given year. And we could find this information for roughly for 16 states in Europe and for 26 states in India. So the method we developed as follows 3 steps. The first relates to the intensive margin, so this short-term component, and we look at the high-frequency covariation between the peak load and maximum daily temperatures. But in our equation, as you'll see, we also include a modulation effect of air cooling prevalence rates in the regions. Then the second step, which is the modeling of the extensive margin, essentially takes place by estimating an adoption function of air cooling that takes into account past climate exposure, income per capita, and urbanization in each region. And we combine the empirical estimates of step 1 and step 2 to then construct projections for the future, taking into account mid-century changes in daily maximum temperature from different global climate models in the ECEMP6 round. So as for the details on step 1, the intensive margin, we take the maximum temperature series and we construct a weather exposure variable that is constructed through intervals of temperature. So we bin daily maximum temperature into 3 degrees intervals, and in this way we construct a nonlinear spline function that tells us indeed how peak load covaries with respect to extremely low, mid or midly cold, or mild, or hot or very hot temperatures. So we have a 3 degrees by 3 degrees interval and 1 coefficient for each of these intervals. And this would be represented by equation number 1, in which indeed we have only temperature, income per capita that is driving the electricity per capita electricity demand, which is our dependent variable, plus a set of controls. And then we augment this equation with our preferred specification that also includes an interaction effect with between temperature, between the spline of temperatures, and air conditioning prevalence in the given region, always controlling for seasonal and other socioeconomic factors. As for the extensive margin, instead, the second component of this empirical framework, we take the annual prevalence. So we have information on from household surveys, but they are aggregated at the yearly level. So we have yearly by state, a yearly by state panel for both Europe and India, and we put these informations together to exploit all the variation in climate and income across the 2 regions. And we assume that IC prevalence is a function of the 10-year moving average of cooling degree days with a 24 degrees threshold. And we take the 10-year moving average because we believe that people, in our theoretical framework, people adapt and buy and purchase new appliances based on the expected climate, which is represented by the climate they've been experiences in the past years. So we also tried different thresholds for the moving average, but we find really no differences. So we took a 10-year moving average of CDDs, log per capita income, and the urbanization rate. And the functional form is a multivariate linear equation with a logic transformation, though, for AC prevalence, because AC varies from 0 to 1, or from 0 to 100%, and therefore we need to include a logistic transformation that gives us nonlinear effect when we actually go to look at the impact of each specific linear component. And we will see how the function is shaped just in a few slides. The final step is doing the projections for future impact around mid-century. So we combine the estimated coefficients from step 1 and 2 with indeed climate change projections. So we take a 5-year representative time step for current and for mid-century epochs for 29 different GCMs. And we take the projections of maximum temperatures and CDDs at the grid cell level. So we can project future air conditioning prevalence as well as future electricity demand dependent on the future air conditioning prevalence at the grid cell level, because we have information on SSP's projections, gridded downscale SSP's projections on income per capita, as well as, of course, climate gridded projections. So we match this information and we have gridded level projections of future prevalence and electricity demand. And then we aggregate this at the state level in order to show you the key implications for different states in Europe and India, taking into account population dynamics in both SSP2 and SSP5. And finally, also, it's not shown here, but we consider two different climate scenarios, climate and socioeconomic scenarios. So SSP2 in combination with the RCP 4.5 and SSP5 in combination with RCP 8.5. Then, in terms of the results that we find, these are the results for the intensive margin. So the variation in the peak load over the temperature distribution, so the maximum daily temperatures. And the value on the vertical axis is the percentage increase in the per capita peak load with respect to the baseline value under thermal comfort. So if you look at the green line, which is the equation 1, the thin green line is giving us the typical U-shaped function relationship between weather and load when there is no interaction component of air conditioning. Whereas in the colored lines and areas show you the differences in the response function when we allow for the modulation effect of air conditioning. That goes from an impact which is still positive for hot temperature days when AC is roughly 0 or 1% to very, very like 2 to 3 to 4 times larger shocks when AC penetration rates, AC prevalence rate in the region are up to 70%, which is, let's say, this is the distribution, let's say, of also what we find in current levels of AC prevalence in some states, particularly, for instance, in rich states, urban states in India, and in southern states in Europe. So you can really see that there's a high heterogeneity when we take into account this modulation effect. The second component of the results is the extensive margin. So on the left, on the figure on the left, apologies, perhaps it's quite small, but you can see the adoption function, in which on the horizontal axis you have we have annual per capita GDP, and the shades represent instead some climatic areas based on the cooling degree days, the historical cooling degree days. So whereas on the vertical axis you see the actual AC prevalence rate, the projected expected prevalence rate, and you can see that in areas in India where you have relatively low annual per capita GDP but high CDDs, high climate exposure, or you have already very high prevalence rate from 25 to 50%, even at relatively low levels of income per capita. Whereas at the same time, in rich states with few CDDs exposure, you have much lower prevalence rate, which is what somehow we were expecting. But interestingly, when CDDs increase, even relatively marginally, from a 15 to a 50 CDDs per year, and these are CDDs with a 34 degrees threshold, so are relatively lower than the typical 18 degrees CDDs. Well, when we shift to this hotter climate, even in Europe, then the projected prevalence rate actually really increases to levels which are comparable to India's low-income, high-climate exposure. So we can then project, based on the methodology explained before, the expected prevalence rate in the different countries in Europe and India. And here you see on the right figure, the gray bars are the actual 5-year average AC in the past 5 years. And the orange is the additional component due to both income and climate effects in the future for the two combination of scenarios between SSPs and RCPs. And so we find that economic...
Yeah, sorry to
Yep.
interrupt you. Just a couple of minutes left. Okay.
Okay, perfect. So I'll speed up, but here we see that income is the key driver behind the growth in AC for India, whereas climate change is going to be the most important driver for Europe. So we use these projections of AC in combination with future maximum temperature projections to show how the peak load will vary with respect to a scenario with no climate change. And here you see on the left the percentage increase in the peak load, and on the right the actual increase in gigawatts. You can see that there is a strong gradient in Europe from north to south, which is typical also in other studies in the literature, but we find 2 to 3 times higher shocks than the previous comparable studies, indeed because we are introducing this modulation effect of adaptation with higher AC use. And just to give you an example, so here you see the composition of the drivers of this change for Europe, and you see that temperature, either through intensive margin short-term adjustment or through extensive margin long-term adjustments, is the most important driver for this total electricity demand increase in Europe due to cooling. But then more interestingly, if we then look at the projections of the peak load, and we only compute the seasonal maximum peak increase in the summer and winter with climate change and with respect to the baseline, and we take the difference with respect to the baseline, we see what I'm showing here, which is that Italy and Spain are the countries that are going to have the largest shocks in terms of cooling, additional cooling requirements in order to adapt to climate change. Although other countries like France still would have an additional peak generation needs of roughly 2 gigawatt, which is not, let's say, a small amount. And in most Central European countries, although cooling and heating requirements compensate, so there's a compensation effect that we don't see in Southern Europe. And here is to show you how then the projection can be really start from grid cell level projections. So we can really then construct estimates of the peak load for any given regional extent. And for instance, we take these type of results for Italy, so the projections of the peak electricity demand for Italy, and we have plugged them in implemented in a capacity expansion model for the country, so only for Italy. And here you can show some preliminary results of this, let's say, separate study. And on the left, you can see the additional generation from different fuels and sources required to accommodate these peak electricity demand increases. And on the right, the additional capacity. So we have an increase in gas generation and in solar generation, depending on the assumptions on gas price. This mix can vary considerably. But importantly, we also have a definitively non-negligible increase in the additional capacity that needs to be installed in order to be able to accommodate this peak requirements. And I'll just close with my last slide on showing again these projections for the Italian case, in which without AC shocks, we have a given set of projections for curtailment, annual system cost, and emissions. And you see two cases with respect to two scenarios for the gas price. And then when we implement the air conditioning shock, we roughly find a 10 to 15% increase, both in the curtailment needs, in the annual system cost, and the emissions. Costly renewables investments, still air conditioning is going to need increases in emissions. And I leave the caveats maybe for discussion, for a few questions, but essentially we want to expand in the type of technologies that we considering also heat pump. And also we believe that insulation and energy efficiency policies that we don't account in this framework can really change the picture and reduce the peak load requirements where they implemented. Thank you very much.
Okay, Francesco, thank you very much for your very interesting presentation. Indeed, we're gonna increase. It's very likely that we're gonna increase the use of AC in certain region of the world, at least. I would like to ask the public if they have any question. Maybe I have like a very quick one. I mean, you just stated in your last slide, but I would like to ask you to elaborate more because you're saying that in 2050 the carbon intensity of the energy mix will be much lower than today, which is right in theory. At least in Europe, we have this European target of climate neutrality. So what what would that be the impact in terms of emission for the BCC? I mean, I don't know if you did already some first level estimations.
Yes, thank you. So for in let's say in the empirical paper, as we don't have we don't implement these shocks in the model, what we did was to develop let's say worst case scenario in which we computed the emissions of the current electricity of the current generation mix of all European and Indian countries if with these additional shocks. So we were computing, let's say, the emissions if the system stayed the same in the next 20 to 30 years, which indeed is a great assumption, but is interestingly just to see the amount of emissions. And we see that overall in Europe, emission roughly balance out. So we have a 2 to 3% increase in emissions. So it's not a story of emissions in Europe because of the compensating effects, but it's really a story of additional costs of investments and of installed capacity generation. So in this, it's a very preliminary run only for Italy here, but you can see that we have actually increases in the system cost and in the curtailment, especially in the case with many renewables. So the one in which we implement a 100 euro per megawatt hour price in gas. You see that curtailment in terawatt hour increases by roughly 20-25%, because we are installing more renewables in order to be able to accommodate peaking cooling needs, but then we actually have then even more capacity in what would be needed right in the other times of the year. So we need more curtailment. So there are these sort of implications are rarely found in the literature. So we really believe that in implementing this type of impacts in capacity expansion and dispatch models can give us idea of different trade-off. Is sometimes maybe not a story of emissions, but can be a story of system implications.
All right, thank you very much. Sorry, I'm a little biased because working in Klima, it's all about emissions, but you're completely
No,
right. It's a matter
but
of
yeah, sorry, I also didn't tell the other part of the story, which is India. I mean, even with mild
of course.
decarbonizations, like the shocks that we implement in India really would increase their emissions by 20% by an amount which correspond to 20% of their current electricity sector emissions. So there is in that region there is instead a huge, let's say, relevance of decarbonizing, also in taking into account this type of additional demand needs. Absolutely.
Okay, I see. Perfect. Thank you very much. Okay, well, I would like to continue for hours, but we need to jump to the as interesting next speaker for the next presentation. Thank you very much, Francesco,
Thank you.
once again for your interesting presentation. I'll invite the people to reach him
Thank you for
to
the
him
questions.
directly. If you have questions, also write in the chat, and we're going to have maybe time at the end of the session to discuss. So I would like to jump to the next speaker. The next speaker is Jan Holland, senior scientist at the Climate Service Center in Germany, GRIX. He's currently researching the energy climate interface, is focusing on identifying vulnerabilities of future highly renewable energy system. He holds a PhD from University of Cologne and he works also as a postdoc at ETH and is a fellow of the interdisciplinary Young Scientist Network, Das Junge SIF. Today he's going to present about his work on climate change impacts on wind energy, evaluating the climate modeling chain. Jan Warland, please come to the virtual stage and the floor is all yours. Thank you very much.
Great. Thanks a lot, Stefano, and good afternoon to everyone. I'll try to share my screen. And then we should be ready to go. So as Stefano already mentioned, my name is Jan Holland, and I work at the Climate Service Center GRIX in Germany, Hamburg. And today I want to talk about climate change impacts on wind energy, evaluating the climate modeling chain. But before we talk about this detailed topic, I want to start a bit more high level. I think there is a consensus emerging that climate should be included in energy modeling. So earlier today, Philip Tulkens said he thinks it's important that we have stronger collaboration of climate and energy modelers. And I think this is also reflected in the renaming of EMPE. And it also manifests in what is written on the homepage, where the organizers say that the increasing role of climate policies and climate change should be considered in energy modeling. Similarly, we wrote a perspective paper recently in Jewel, which is an outcome of another workshop, the Next Generation Challenges in Energy Climate Modeling workshop, in which we argue that we need a new approach to bring energy system and climate modeling together. And in particular, we say that we have to not just use climate information, but to make sure that we use it effectively and appropriately. So the question really is in the detail: how exactly do we bring climate information into energy modeling? And that's what I want to talk about today. I will focus on the climate modeling chain, and I want to briefly introduce you to the concept in case you're not yet familiar. So assume you're interested in the impact of climate change in a particular wind park. So we start at the very right here. In order to investigate this, you need high resolution climate information for that park site. And you don't get that out of a single climate model, but what you need is a climate modeling chain. So the way this works is you start with a couple of scenarios, which include greenhouse gases, land use, aerosols, and so on. And these scenarios are then fed into a global climate model, which models the entire planet and gives relatively coarse resolution information. And with that information, then a second climate model is run, which is called the regional climate model, which gives you higher resolution information that is believed to be better suited for particular applications on a local scale. This is all complicated by the fact that there are multiple scenarios. There's approximately 30 or so different global climate models and another 10 to 20 regional climate models. So it's really a large amount of data. And the question today is, what exactly happens to wind speeds in the process of downscaling? So what happens to the climate change signal between the global model and the regional climate model? Because what we would expect is that from the regional climate model, we get higher resolution, but the large-scale features should be the same in the global and the regional models. However, when we look at the models, we find that the reality is different. So these two lines show you output from global models in the upper line and then regional climate models in the lower one for three different future climate change scenarios. And the colors mark the change in wind speeds at the end of the 21st century minus the end of the 20th century. And it's quite obvious that in the upper row, we have reductions over land, for example, here in Eastern Europe in RCP 4.5, which do not exist in the lower row. So that means in the global climate models, there is they project a reduction in wind speeds that is not captured in the regional climate models, which is surprising. The second feature we see is that offshore, there's actually quite good agreement between the two, and they project reductions in wind speeds over the ocean, which become stronger from the weak climate change to the strong climate change scenarios. So let's try to understand what's happening here over land in Eastern Europe. I will, on the next slide, have the upper part of this plot again, and then add in the lower part the so-called land use forcing. So this is the changes in land use that are fed into the global model. And just from visual comparison, it's quite obvious that the upper and the lower patterns are fairly similar. So for instance, again, RCP 4.5, the reduction in wind speeds in Eastern Europe is parallel by a large area of increased land use. So this is, to be specific, it's an increase in primary plus secondary land. So that is land recovering from human intervention. So these patterns match together pretty well, and also from a physical point of view, it makes sense if there is more forests and vegetation, then the surface roughness is higher and the wind speeds are lower. We also tested this statistically, and it turns out that our eyes don't fool us here. there is indeed a fairly good correlation between wind speed change on the y-axis and the change in land use on the x-axis. So that explains the signal we see in the global models, but why does it not exist in the regional models? And here the answer is surprisingly simple. It's because the regional models use constant land use. And that is because the data that would be needed to run them with varying land use didn't even exist until earlier this year. So it was recently developed, and it is even unclear whether the next generation of downscalings, so the ECEMP6 downscalings, will use time-varying land use. So from a user point of view, what that means is that the scenario assumptions are not the same. So even if you look at RCP45, for example, even though the scenario has the same name in the global and regional models, it's not the same scenario because it uses different forces. Okay, let's go back to the first figure I showed you already. We now understand the discrepancy onshore. That is due to land use change. But what happens over the ocean, and can we understand this better? Now, what I want to do is to look at an example here first. So this is offshore wind in the United Kingdom. And now I don't show the ensemble mean, so not the mean over all the different climate models, but I show all the models individually to illustrate how uncertain the climate change signal is. So now each color here is a different global climate model. This one, for example, is called HUTGEM. And then there is 6 different regional climate models that downscale the global climate model. The important take-home message here is there's really a large spread. So in RCP26, for example, anything between 0.05 meters per second increase or 0.4 meters per second decrease is possible given these climate model simulations. That means, in particular, because the spread also goes to positive values, it means that the signal is often not robust. But if the values at the lower extreme would be highly relevant for wind energy. So for example, here a reduction of 0.6 meters per second or even more than that would be very relevant for offshore wind energy. So we see this huge spread here, and the question is whether we can use physical reasoning to constrain the spread better. Is there any way to better understand why the disagreement is so large? And one, first order physical reasoning could be that it's related to the general circulation. This sounds complicated, but it isn't. So essentially, the circulation in the atmosphere is driven by temperature differences, in particular the fact that the equator is a lot warmer than the poles. And this drives the general circulation. However, now we know that climate change leads to more warming over the Arctic as compared to the equator, which you can see here in this figure from the IPCC Assessment Report 6. And that means if the pole warms quicker than the equator, it follows that the temperature gradient gets weaker, and that means that the circulation could also be weaker. So this reasoning makes physical sense, but of course it's highly simplified, so we should check whether the data agrees. And to run this check, I used the same data I showed you before, so these plots of all the different climate models, but now I sort them differently. So the y-axis will still be the change in wind speed, but then the x-axis is the change in the temperature gradient. So each of these models, for example, the HUTGEM one we had here, will now have a value corresponding to the projected temperature gradient change. If we do that, this is what we get. And this looks like a surprisingly linear relationship. So the correlation coefficient, for example, is 0.9, and it also seems like a pretty good match. What is also interesting is that if you look at one individual scenario, for example, the RCP 8.5, there's a huge spread in changes in the temperature gradient. So anything between -11 degrees and -3 degrees is possible given the model projections. So there's a lot of uncertainty with regard to these temperature changes. But once you fix the temperature change, there's a lot of agreement regarding the expected wind speed change.
Jan, a couple of minutes left for your presentation. Thank you.
Okay, cool. Good. So this was an example for the UK. I repeated this for the other countries as well. And long story short, you find similar results in other resource-rich European countries like Ireland, Norway, and Germany. And to have a more systematic spatial view, I also plotted this on a map where you see that correlation between the temperature gradient change and wind speed change is fairly high pretty much everywhere in Europe that is suitable for offshore wind. And the amplitude is somewhere around 0.02 to 0.1 meters per second. So that means we can expect wind speeds to drop by 0.02 to 0.1 meters per second for every degree of temperature gradient change. As I said earlier, this is for the ECEMP22 models that are downscaled in Eurocordex. And if we double check this with the newer ECEMP6 models, we get a qualitatively similar story, but the values are a bit weaker. Both the correlations are weaker and also the amplitudes are weaker. But still, the general story seems to persist. And with that, and in the interest of time, I would like to wrap up. So there are two important drivers when it comes to wind speeds changes in Europe. One is land use change, the other one is the equator to pole temperature gradient. And onshore, there's a big discrepancy between the global and the regional models because of land use change. And that means exclusively relying on the regional models equates to underestimating climate risk. So one should complement and use both data sets. Offshore, both are actually tell the same story. Offshore winds are expected to decline, but there's a large spread between the models, which, however, can be understood in terms of uncertainty in the temperature gradient. And with that, I would like to thank you for your attention and looking forward to more interesting discussions.
Thank you very much, Jan, for keeping the time and for the very interesting. It's really nice result to have this correlation between the change in temperature and the change in offshore wind speed. While I invite the public to ask more questions in the chat, I have a quick question on the difference between the regional and the global models for the onshore wind. So basically, you state that one of the main problems of this discrepancy is the the missing link on the land use change. How would then the regional models can be improved to avoid this discrepancy in the future, for example?
Yeah, I mean the first thing is we just have to be aware of this shortcoming of the regional models, because the missing land use change means that they tell a completely different story than the global models with respect to long-term wind speed changes, and that is problematic because for high resolution assessment, people tend to only use regional climate models and then they miss the rest. One can improve this by having varying land use change, and that's a task for the regional climate modelers that they have to implement this in their models, and they are working on it.
All right, thank you very much, Jan.
I have a question, if possible.
Yes, please, Youssef, go ahead, please.
Yeah, thanks, Jan, for the interesting presentation. I'm from a question from someone who's coming from the energy background and as an energy modeler, which I don't have much experience on the climate modeling itself, but I'm a user of the climate outputs. So what would be kind of a useful practical tip to account for these kind of uncertainties in energy models, and what would be the best practice in this case, especially if you don't have the luxury of running several scenarios or tens of scenarios.
Yeah, that is a great question. And also that's a systematic problem we have, because energy modeling and climate modeling used to be two completely different things. And now we have to suddenly bring them together. So you're not the only one, but like everyone is having similar questions. I mean, the pragmatic approach would be to use as many models as you can, including regional and global ones. Let's just try to sample as much of it as possible.
Thanks for the feedback.
All right, thank you, Jan, once again for the presentation and the answer to the questions. I would like to move to the next and last speaker of this session. So she's Johanna Sietarts. I hope I pronounced it correctly. Sorry if I don't. She's a doctoral researcher at the Potsdam Institute of Climate Impact Research, PIK. She's analyzing policy instruments that are needed for the Germany's and Europe transition toward climate neutrality. Special focus on the impact of myopic decision making on transformation pathways. Before that, she works. She was a former colleague of us. She was a Director General for Climate Action of the European Commission, and as well as the Poland's Ministry of Climate and Environment. Today, she's gonna present her paper on aligning long-term climate goals with short-term policies, and answering to the question is that how robust is the EU ETS against decision makers' myopia? So Joanna, please come to the stage, and we are looking forward to your presentation.
Many thanks, Stefano, for the introduction. I'm just sharing. Okay, perfect. I hope you see the slides.
Yep, it's perfect.
Okay, great. So welcome to my presentation under the title, How Robust is the EU ETS Against Investors' Myopia? As Stefano said, my name is Johanna Sietarts, and I work at the Potsdam Institute for Climate Impact Research in Germany. And because it's Friday afternoon, 4 o'clock, I would like to start this presentation with a question to all of you. And so imagine you have a company and you need to take some difficult decisions that might put your company at risk for the present moment, but you need them so that your company does well also in a couple of years. The question is, how far ahead into the future would you plan? You can also imagine yourself being a politician, and again, you need some strategic decisions, but you also want your voters to remain happy for the present moment. So how many years ahead would you plan? I give you two options. Would it be rather something like 10 years or rather 30 years? So that you get a better intuition of what it means to plan as far into the future, let's have a look at a few historical events you would have missed if in the past you were planning 10 or 30 years ahead. So for 10 years, we had Brexit, we had COVID, we still have the war in Ukraine. For 30 years, so we are somewhere at the beginning of the 90s, you would have missed few global events such as the invention of the World Wide Web, the fall of the Soviet Union, the financial crisis, Brexit, COVID, war in Ukraine. So feel free to write in the chat 10 years or 30 years, and I will have a look at your responses after the presentation because I don't have the time now. And as for now, I would just presume that most of you would choose the option of 10 years because, well, this is the starting point of my talk today, is that many actors, companies, politicians, but we all, we usually act myopically. So we plan only a few years ahead when taking decisions. And why is this all a problem? Well, what might be a problem is that there will be potentially a certain mismatch between how most energy models work and then real decision making happens. So here you can see a typical energy modeler. We really like to look far ahead into the future, for example, to 2050 or even till 2100. However, in real life, many decision makers will plan the transformation or investments only looking a certain period of years ahead. And because of this, it might lead to a different transformation than the one predicted by our perfect foresight models. Different, does it mean better or worse? Well, mathematically, it's possible to prove that for the kind of optimization problems that we solve, perfect foresight will always lead to the cost optimal solution, so to the better solution than myopic foresight. And the question that now arises is, if we have this kind of mismatch, what if we used, next to our perfect foresight models, also myopic models to simulate this real decision-making behavior and design policies that would be more robust against this myopic behavior? And this idea is not completely new. There is, for example, one great study using a myopic model and showing that exactly myopia can result in delayed climate action and higher total transformation costs. There are some studies using myopic models for computational reasons, but as far as we know, there are no studies that would actually use myopic and perfect foresight models together to analyze some concrete policy instrument. And this is now where our work comes in. So we want to apply this idea and analyze the EU ETS, which is obviously a super important climate policy instrument of the EU. And I've split the research question into kind of two parts. So the first part would be, we want to see how myopic behavior would impact the functioning of the EU ETS and also the resulting energy investments in the energy sector. And then the second part would be, after we've analyzed, more theoretically what would myopia imply for the EU ETS, to take a step back and to look at the current state of the EU ETS and to see if myopia is actually an issue. And just as a teaser, we have some interesting results on EU ETS prices and why they might have increased that came out of our analysis. So stay till the end of the presentation if you're interested in it. So let's go on. Regarding methodology, how did we do our study? So at my institute, at PIC, we already have a model that is called LIMES that is very well suited to analyze the EU ETS. It covers all EU ETS countries, all ETS sectors. It is a perfect foresight model. And what we did was to implement, to develop a myopic version of this EU ETS model. Basically, it means that instead of solving one long optimization problem, as in the perfect foresight case, we apply a rolling horizon. So we solve the optimization problem for the first 10 years, then we move forward, and so on. And between those optimization horizons, we always need to store some variable values. We continue till the end of our time scale. Now let's move on to the most important results that we have obtained. So the first part is, in theory, if there is myopia, what would it imply for the EU ETS? First of all, regarding emissions. So here you can see on this plot the difference between the budget regarding the certificates that are available for a certain period of time and the emissions planned to be emitted by the model. So perfect foresight, and on the right here in yellow, myopia. And the main difference is that the perfect foresight model will anticipate the future. So it will already, quite in the beginning of the transformation, it will plan to emit less than it would actually be possible regarding the number of certificates available. On the other side, the myopic model will always plan just to emit as much as possible, so use up all certificates that are there. And because of this, when we look at the total cumulative trajectory of emissions, even if we have the same end goal, there will be a delay in the case of myopic behavior. what will it mean for CO2 prices? So regarding CO2 prices, as I said before, so myopia will emit in the beginning more, but there will be a certain moment in time when it will have used up already more certificates and will need to kind of catch up with the perfect foresight model. So it will need to emit less towards the end of the transformation. And this is why there will also be a different CO2 price trajectory resulting if we assume that compliance actors are myopic. So in the beginning of the transformation, the CO2 price will be much lower, but then towards the end, it will be much steeper. Now, the last part of this first part of the results concerns the energy investments. What does it mean actually for the energy sector of the EU if actors would act myopically? So here, first of all, you can see a graph. So it's the total wind capacity in whole Europe plotted over the years. And you can again see that there will be a delay in renewable capacity expansion, which is quite large, especially here in the next 5 to 10 years. And similarly, regarding fossil fuels phase out. So this is a plot showing the amount of coal in the electricity mix. And again, in the case of myopia, coal will stay much longer in the electricity mix than in the perfect foresight model. And let's remember that the perfect foresight trajectory is the cost optimal trajectory. So this is actually where we would like to be in the ideal case. Now let's move on to the second part of the results. So now we've analyzed quite theoretically what would myopia imply for the EU ETS. And the question is, but what about the current state of the EU ETS? Is myopia actually an issue, or is it maybe not an issue? So here you can see the CO2 price trajectory estimated that is necessary to reach the Fit for 55 goals. So it's really the newest kind of EU targets regarding the EU ETS and also regarding the market stability reserve for the case of perfect foresight and the case of myopic foresight. And what you can notice is that in the case if actors were myopic, our model estimates then that CO2 prices would be, as of today, actually still quite low because there are still many certificates in circulation. So if actors would not anticipate scarcity in the future, the CO2 price signal would be still very weak as of today. But you all know that CO2 prices actually increased quite a lot over the past few years. Here you can see the real CO2 prices on the EU ETS. And so it's very interesting because they actually correspond quite well to our perfect foresight trajectory. So the ideal cost optimal trajectory of our our model. And what does it mean? So it means that our hypothesis is that probably as of today, actors are actually not myopic on the EU ETS. And a possible explanation would be that they perhaps used to be myopic in the past, but due to stronger political commitment to climate targets, they changed their foresight here and actually really believe and trust in EU climate policy, look far ahead. And this is why prices also increased as much. But this is only part of the whole picture, because obviously there have been many reforms in the past years. So with here you can see the perfect foresight CO2 price trajectory. Here again in green Fit for 55, and here in gray to reach the targets that were there before Fit for 55. And you can see that there is really a strong jump. So the ambitions now are much, much higher. And if we bring together those results, we see reasons to believe that prices perhaps increased due to reforms, because Fit for 55 really sets much more ambitious targets, but also a gradual shift from actors' myopia to long-term foresight. And now you might ask yourselves, well, so it means that actors are not myopic anymore. So all the risks that I presented to you before are actually not really problematic or not valid. Well, we still see reasons to be quite carefully optimistic because as you see, the fact that prices are as high today really depends on the expectations compliance actors have about the future. So if the prices are high because actors look far ahead, it can also mean that if actors become myopic again, prices could drop. And this is what we've also analyzed in Iran. What would happen if we believe that, so here this changing foresight trajectory, actors were myopic in the past, they became farsighted as of today. But if their behavior changes, why could it change? It could, for example, change if climate ambitions of the EU get weakened, for example, in light of the current energy crisis or another crisis that might come. Potentially, prices could really drop strongly again. So we should still consider the risks that I've presented to you before. Now let's summarize. So first of all, I want to say that we do think that myopic models can be useful to test robustness of policies, and they are not really used a lot yet in energy systems modeling. Then regarding the first part of our results, is the EU ETS robust against myopia? So technically, not really, because we see some problems. So the CO2 price signal can be delayed, the decarbonization can be delayed, and that's why our policy recommendations would be, well, first of all, kind of what has been done in the EU ETS in the past, backloading of certificates, so taking them in the beginning of the transformation and putting them back on the market later on can help because it can prevent this delay of the CO2 price signal. And also having additional policies that ensure that renewables still get deployed and that fossil fuels still get phased out so that we approach our cost optimal trajectory from perfect foresight and prevent those delays that might occur if actors act myopically. So these additional policies are still very important. But then looking at the current state of the EU ETS, we see reasons to believe that current CO2 prices are actually just right. They correspond quite well to what our model predicts is necessary to reach the targets proposed by the climate law, so Fit for 55 and climate neutrality in 2050. Actors seem to look far ahead, which is a positive development because it means they will drive like cost-efficient and green investments already now. But at the same time, we need to be aware of the fact that the fact that prices are high now does not mean that they will always stay high. There is no fundamental instrument ensuring this. So it's a really labil equilibrium of how the CO2 prices are. They could potentially drop again. And this is why, the recommendations would be, we don't see really reasons to put a strong price cap on CO2 prices. Any entrance into the market should be carefully assessed because of this not very stable equilibrium. And again, additional policies are still useful. So thank you all for your attention, and just wanted to mention that we will soon publish or soon submit those results and perhaps publish a preprint, so stay tuned for this. Thank you.
Thank you very much, Joanna, for your presentation. Interesting result indeed. A lot of policy insight in here. While I invite the public to write their question on the chat, I have a question for you. So I imagine this study has been done, let's say, before or before the war, like the start of the war, and you also see that also because of the war and the Repower EU, there has been some political action not only for decreasing the gas but also for intervening slightly in the ETS. what would it change in your study? The fact that like we had the war, so like you change a little bit the geopolitical situation. What would be the impact on the ETS prices and the foresight?
So yes, the study was mainly done before the war. So I would say that this geopolitical situation could have had a really high impact on how actors behave, on how, I mean, every time such a crisis happens, prices on the ETS drop for a moment, like on all markets. But at the same time, I would say that we saw that the EU reacted quite rapidly, ensuring that, well, we have this energy crisis, we have this geopolitical situation, but it does not mean that we will lower our climate ambitions. And I think this was a very important message, because we can see that prices are still kind of stabilizing. And I think this was the message sent to compliance actors, that well, you still need to plan far ahead. So I would say that regarding the foresight or the prices, it looks like the situation is stable. It looks like it didn't affect it too much, but yeah, we don't know exactly what can happen.
Yeah, perfect. Thank you very much for your answer. There's a question from Jan Holland. The question is, how do you model the integration challenge? Could it be that real actors simply bet on high electricity prices in the next years and a low cannibalization effect, and thus want to be fast?
Jan, could you perhaps explain what you mean with integration challenge? Because I'm not sure if I...
Yeah, sure. Maybe the question doesn't make any sense, but and great talk, by the way. So what I wondered is, so you had the separate price evolution in the myopic and the perfect foresight, and then you added this curve of what happened in reality, which is closer to the perfect foresight and quicker action than in the myopic. And I wondered whether, like, why that is the case, and whether it could just be that well, investors now want to have their wind park online really quick, or want to act really quick because there isn't a lot of renewables yet competing at the same time. So whereas in the future there will be more cannibalization, so they all generate at the same time because they're exposed to the same weather. So at the time they generate, they might have lower revenues. I just wondered whether that could be an explanation.
I'm not really sure that I get it, that I understand it completely. So I mean, because right now there are not as many not as many actors kind of participating in the, or I don't know if I understand the question.
Maybe we follow up later. Maybe my question doesn't make sense.
If I may very briefly try to make a connection here, if I understand correctly. I mean, Jan, if I understand you, you're talking about actually like renewable deployment, whereas Joanna was talking about the carbon price. And there is some interaction, but I think like this, putting them fast on the ground for the crisis, that will only influence renewable and would potentially rather drive down carbon prices, because you might have less demand for permits, although more coal dispatch might also drive it up again. So I would say there are two different aspects that are not directly related.
Maybe I can also add this also to be thought that the ETS cap will decrease in the future, so somehow will be proportional. So like we'll also compensate this effect of having less demand for carbon certificates because there's more renewables. But then that's something that we'll see in the future. There's also another question from Youssef. Youssef, you can also jump on the stage and ask yourself if you want.
Yeah, thanks for the opportunity. And thanks for the interesting presentation, nice visualization. The first question is kind of a bit maybe philosophical. How would you define the robustness in this context? And the second question, what is the time interval that you would suggest to introduce these myopic acts or events into the model? Every year, every 5 years, or what is the best time domain in this case?
Yes, so I will start with question number 2 regarding the time interval. So for now, we have a model that operates in 5 years time steps. So we're limited to, we have this kind of constraint, we cannot go below, below 5 years steps. And so what we do is we have 10 years foresight, and every 5 years we revise our decision. So we move always 5 years forward, and we assume actors look 10 years ahead. Of course, you can test all different, you can do everything in between myopia and perfect foresight. You can assume they are looking 20 years ahead or 15. I think if we would have a model with a higher time resolution, it would be also interesting to have even shorter time periods. So then also you can, because 10 years is actually still quite long. So it would be, I mean, there's no clear right or wrong, right? It depends on the assumptions, but would be interesting to test all those different, to have all those different possibilities. And regarding question 1, well, robustness, as you say, it's a very it's a big word. So in my work, in the end, what I look at is, I assume that the perfect foresight model shows us the cost optimal trajectory. So this is the trajectory you would want to have in the optimal case. Of course, we do not take into account facts like, okay, there can be some major shocks happening. So if you would have a model and also test really how a trajectory, how a transformation pathway is robust against some shocks, this would be even better. But in my case, I kind of just assume, okay, we want to be as close to the perfect foresight trajectory as possible, because this is the cost optimal transformation. And then myopia, if you do the myopic simulation, you have a certain gap. So basically, and this gap can be either smaller or bigger. So if it's very small, and if we have some additional policies ensuring the fact that this gap gets smaller, I would say, okay, in total, we have a robust mix of policy instruments. But of course, this can be further, expanded into many directions.
Thank you. Thanks for the insight. Thanks.
Thank you very much, Joanna, for the question. Maybe we have just 1 minute left, but very quick question for Magnus that he actually is directed to Jan. I will repeat it. Is this effect similar across wind speed, or is one or the other tail more affected? Regarding to the previous talk, Jan, if you could quickly answer to that.
I would have to check, Magnus. I think the on land, it should the drag scales with the wind speed, so the high wind speeds should be more affected. Over the ocean, I don't know, but I'll come back to you.
Okay, thank you very much, Jan. We are perfectly on time, so I would like to conclude this session, thanking all the speakers. Thank you, Seth, thank Francesco, thank Jan, and thank Johanna. Also the organizer, and of course everybody that assisted in this last parallel session. So I think now there's a short break, and then it's going to be like the closing session of this very fruitful conference. Thank you very much. Have a nice ending of the conference and a nice weekend. Bye-bye.